Hey there, scientists. Here are the calculations for the motion lab. The video is a bit long, so feel free to skip around to what you need to review. Good luck. I'm here to go over the motion lab with you so that you can all see how to do the calculations properly before your quiz tomorrow, or Monday if you're due period. So here we have our instructions and our important formulas. Remember that your distance equals rate times time formula, or your DIRT formula, can be rearranged. So if you want to solve for a rate, you simply just divide each side by t, and you get rate is equal to distance divided by time. Where rate, let's remember, is either velocity or speed. Also, our acceleration formula might look slightly different than what we've been using in class, but time here is the same thing as time final minus time initial, so we could rearrange this as v final minus v initial divided by time final minus time initial, or you can say that velocity you end up with minus the velocity you start with divided by the time you end up with, let's make that a better looking f, and the time you start with. Let's remember that velocity is measured in meters per second, time is measured in seconds, so those units come out to be meters per second squared. Forgot to do that for our velocity, so let's check our units there. Our units for distance are meters, and our units for time are seconds. So always remember that our velocities must be reported in meters per second, and our accelerations must be reported in meters per second squared. All right. If you remember, during our first activity, we walked for 10 meters. So let's say that I, Mr. A, Mr. Moore, Miss Metzler, Dr. Nagel, all did the lab together. So we know our first activity, we all walked 10 meters. Let's say that I took 2.5 seconds, Mr. Moore took 2.3 seconds, Metzler took 2.2 seconds, and Nagel took a flat 2 seconds. What we can then do is calculate our average speed for each one of these trials. All we simply do is divide. If we remember our equation for rate, we've solved for rate or speed up here. Our equation is distance over time. So all we have to do is divide 10 meters in this case. Sorry, jumped around a little bit there. All we have to do is divide 10 meters in this case by 2.5. So let's pull up our calculator. You'll be allowed to use a calculator. Distance, 10 meters divided by 2.5 seconds, and we get an average speed of 1.6 meters per second. Let's go ahead and calculate Mr. Moore. He walked 10 meters in 2.3 seconds, and that gives us 4.3 meters per second. I don't think I did my calculation correctly, so let's do that again. Mr. A, which is 10 divided by 2.5, was 4 meters per second. That looks right, so let's go ahead and fix that. My apologies there. 4.0 meters per second. Let's go ahead and do Mr. Moore. 10 divided by 2.3. is equal to 4.3 meters per second, so a little bit quicker. 10 divided by 2.2 for Mrs. Metzler, 4.5 meters per second. And 10 divided by 2, which we know will be 5, for Dr. Nagel. Now, speed and velocity are the same thing, except for one important fact. vector, or velocity, is a vector. Velocity is a vector. So let's say that we were on this outfield of the softball field and we ran from the dirt there towards the flagpole. On our campus, that's north. So the only difference here between speed and velocity is that direction. So 4.0 meters per second north, 4.3 meters per second north, 4.5 meters per second north, and finally 5.0 meters per second north. What we can then do next is calculate our acceleration. So our acceleration is our velocity final minus our velocity initial divided by our time final minus our time initial. And we all know that equation by now, or at least we should, hopefully we do. And all we have to do is plug in our average velocity for v final, because that's the velocity we ended up with in this particular case, because we walked from 0 to 10 meters. We started at a stop. So we know our initial velocity in this case will be 0, and our initial time will also be 0. So velocity final was 4.0 meters per second, divided by our time, which for me was 2.3 seconds. We have meters per second divided by seconds, so we can go ahead and write our units right away as meters per second squared, so we don't forget those. Remember, units are very important. And we can do that math. 4 divided by 2.3. 4 divided by 2.3 is 1.7 meters per second squared. And remember, for this particular lab, we didn't have to do all the calculations. We only had to do calculations for ourselves. So let's go ahead and take a look at that chart. Let's see how we did my calculations. We wrote down our distance, we wrote down our time, and then for average speed, we did distance over time. And I didn't show my work there, so let's show my work quickly. So rate equals distance over time. Our distance was 10 meters, and my time was 2.3 seconds. 10 divided by 2.3 is 4.0 meters per second. 4.0 meters per second. All right, let's move on to activity number 2. For this one, let's move on to activity 2. For this one, we ran 10 meters instead of walking 10 meters. So I'm just going to show you the calculations for me. So the distance we ran stayed the same, 10 meters. Let's say that it took me 1.5 seconds to run those 10 meters. My speed, my rate, is equal to distance divided by time, which is 10 meters over 1.5 seconds. So we can pull up our calculator. 10 divided by 1.5 is equal to 6.6 repeating. So let's round that to 6.7 meters per second. That's our average speed. And our average velocity is 6.7 meters per second north. We can calculate my acceleration using that average velocity. So we know v final minus v initial divided by t final minus t initial is equal to acceleration. Again, we started from a stop, so our v initial is 0, our t initial is also 0. So our v final is 6.7 meters per second divided by 1.5 seconds, and what we get is 6.7 divided by 1.5, 4.5 meters per second squared. 4.5 meters per second squared. Go ahead and fill in the chart there. And let's move on to our third activity. So this activity was the most involved. This is where we measured time, or the time it took us to run 30 meters. But instead of measuring that entire 30 meters, we measured time at 10 meters, measured time at 20 meters, and 30 meters. So let's say it took me 1.2 seconds this time to run 10 meters. It took me 2.0 seconds to run 20, and then it took me, I got pretty tired, 5 seconds to run the entire 30 meters. So what would I do to find my average speed? I would use R equals D over T, where distance is, so for average speed, this is our entire distance. So this would be 30 meters. 30 meters divided by our time, which is our time to run the entire thing, 5 seconds. So 30 divided by 5, we could have done that one in our head too, is 6. 6 meters per second. So let's go ahead and write that down. 6 meters per second. And our average velocity is 6 meters per second north. 6 meters per second north. All right, so not so bad, not too different from our other calculations so far. But once we get into these questions down here, it gets a little more difficult. Our first question asks, what was your instantaneous speed during the first 10-meter portions of your run? In this case, we're talking about that 30-meter dash. So we ran 30 meters, and we timed how long it took us to run 10 meters, 20 meters. We'll mark 0 meters just for good practice there. And we're interested in the speed, or the instantaneous speed. So instantaneous just means at a given time. So we're interested in the speed between, let's call this A and B, the first 10 meters of our journey. So our speed for that first 10 meters, what we need to do is we need to divide the time it took to run this 10 meters divided by the distance, and we know that distance is 10 meters. So rate equals distance over time, where distance in this particular case is 10 meters. And I have to scroll up to check my time, I don't remember. Our time for 10 meters was 1.2 seconds. 1.2 seconds. Let's go ahead and fill that in. 10 meters divided by 1.2 seconds. 10 divided by 1.2, let's pull up our calculator. 10 divided by 1.2 is equal to 8.3 meters over seconds. Moving on to number 2. Number 2 asks for the instantaneous speed for the last 10 meters of our run. So let's go look at this timeline we've already drawn up here. We know that it took 2 seconds for us to run to 20 meters, and it took 3 seconds, that's wrong. It took 5 seconds for us to run a total of 30 meters. So what we're interested here is how long did it take us to, or what was our velocity between that 20 and 30 meter seconds section. So rate equals distance over time, where our distance is 10 meters because we ran from 30 meters or from 20 meters to 30 meters, and our time is 5 seconds minus 3 seconds. So it took us 2 seconds to run that 10 meters. 10 divided by 2 is 5 meters per second. So our velocity, or our instantaneous speed, because we didn't put any direction, is 5 meters per second in that case. So let's look at 1 versus 2, the first 10 meters versus the last 10 meters. The first 10 meters we ran in 8.3, at a rate of 8.3 meters per second, and our last section we ran at 5 meters per second. So our first 10 meters was faster than our last 10 meters in this particular case. So we know that our first 10 meters was 8.3 meters per second. Our last 10 meters was 5 meters per second, but we don't know our middle section yet. And we need to calculate that in order to figure out where we were running the fastest, the first 10 meters, the second 10 meters, or the last 10 meters in question number 3 here. So let's go ahead and calculate that. We know, we can redraw our timeline here. So 10, 20, 30. No, we should probably put 0 in there too. So from 0 to 10 meters, it took us 8.3 seconds. From 20 to 30, it took us 5 seconds, but we don't know 10 to 20 meters yet. So let's go ahead and figure that out. We know our time at 10 meters was, let's see, our time at 10 meters was 1.2 seconds. 1.2 seconds, and our time at 20 meters was 2 seconds. So our rate equals distance over time, where our distance in this case was 10 meters, and our time was 0.8 seconds. How did we get that 0.8 seconds? We took 2.0 seconds and subtracted 1.2 seconds. 10 divided by 0.8, meters divided by 0.8 is equal to 12.5 meters per second. So this one was 12.5 meters per second, making it clearly the quickest section of our run. Number 4, what was your acceleration from the starting line to the 20-meter mark? So we have our run from 0 to 30, 10 meters here, 20 meters here. And what we're trying to calculate is the acceleration from here to here. So we know that acceleration is equal to v final minus v initial divided by t final minus t initial, or again, the velocity you end up with minus the velocity you start with divided by the time you end up with minus the time you start with. And what we're going to do is plug in the proper units there. So we know, or the proper numbers there, we know that velocity initial and time initial are going to be 0. So we can just get rid of those variables. Velocity final, in this case, is our velocity at 20 meters. Our velocity at 20 meters was 12.5 meters per second. We already calculated that. Our time final was 2.0 seconds. So all we need to do is divide those two things, 12.5 divided by 2.0, and we get 6.25 meters per second squared, and that is our acceleration for number 4. Number 5, assuming you continue to accelerate based on your answer to number 4, so based on your answer to number 4, let's write that down, 6.25 meters per second squared. What would be your velocity after 10 seconds? So let's think about this. This one's hard. It's asking us for velocity. We have an acceleration. So what I suggest is you write down an equation that has both of those things in it. And in this case, our acceleration equation has both of those things in it. We know acceleration is 6.25 meters per second squared. And we know that our velocity final, or actually we don't know, we're asked for a velocity in this case, so we can leave VF there. We start from 0, so we can just plug in that 0 meters per second. And our time final is given here as 10 seconds, so we can go ahead and write that down, minus 0 seconds. So we have 6.25 meters per second squared is equal to VF over 10 seconds. We can solve that relatively easily. We multiply both sides by 10 seconds over 1. 10 seconds over 1. 6.25 times 10 is 62.5. Seconds cancel out here, or one of our seconds cancel out here, so we're left with meters per second. So that's how quickly we would be running if we ran at an acceleration of 6.25 meters per second squared for 10 seconds. Number 6. How much more or less did you accelerate during the last 10 meters compared to the first 20 meters? All right, so it's asking us to compare the acceleration between 2 points on our journey, on our run here. So our last 20 meters, so from 20 to 30 meters, so the portion of this run, versus this portion, from 0 to 20. So we need to calculate our acceleration here and our acceleration here. So let's call this A1 and A2 just so we can refer back to it. A1 is equal to velocity final minus velocity initial divided by time final minus time initial. And same for A2. So our velocity final in this case is our velocity at 20 meters. Luckily, we've already calculated our velocity at 20 meters. Our first, and that is right here, 12.5. So we're going to plug that in. 12.5 meters over seconds divided by, minus our initial velocity, which is 0 meters per second, divided by our time final, which at 20 meters was 2.0 seconds minus time initial 0 seconds. So that's 12.5 divided by 2, which is equal to 6.25. So 6.25 meters per second. For our first section, our second section would be from 20 to 30. So we need our velocity final. Our velocity final in this case was our average velocity at 30 seconds, which we have up here as 5 meters per second, minus our initial velocity, which is at 20 meters, which we have as 12.5 meters per second, divided by our time at 20, our time at 30, which was 5 meters per second. So let's go ahead and erase that 2 and put in a 5.0 seconds minus, I think I said meters per second, but it's 5.0 seconds minus how long it took us to get to 20 meters, our initial starting point. So we started from 20, went to 30 in this particular case, minus our 2.0 seconds. So 5 minus 12, 5 minus 12.5 is equal to, that's not correct. 5 minus 12.5 is equal to negative 7.5 meters per second, divided by 3 seconds. So we get an acceleration of negative 2.5 meters per second squared. What does that mean? That means that we slowed down towards the end of the race. I got pretty tired. Running 30 meters was hard. All right, number 7. I'm going to trust that you guys could compare average velocities for your group mates. What you do to calculate average velocity is rate equals distance over time. For this particular example, I didn't give you time for all of our group mates. So I think you guys should be able to do that. If you have questions, let me know. Number 8, even though it seems intuitive, why does all motion depend on reference points? We talked about this. Remember with the video with the guy with the long hair, the crispy lettuce on the skateboard? So if he threw up the ball and he was looking at it, it looked like the ball went straight up and then straight down. But if you looked at it from the side, you would see that the ball traveled in a parabola. So depending on your reference point or from which you view motion may look different. So you could write that nicely in words. So let's say motion depends on how you view it. Another way we could think about that is with our cars. So let's say that we had two cars traveling on the highway right next to each other. If all you could see was that car, these are some poorly drawn cars, then you wouldn't think that either car was moving at all, right? Or let's think about that tree outside our window. So we have a tree outside our window. Is that tree moving? Well, it depends on your reference point. If it's from your reference point, no, because you and the tree are moving at the same speed. We're all traveling around the sun at approximately the same, or at the same rate. But that tree relative to the sun is moving. That tree relative to you is not moving. So if the reference point is the sun, we would say, yes, there is motion. If that reference point is you, you'd say, no, of course not. That tree's not moving. It's not group. All right. How many feet did you run in total? 1 meter is 3.3 feet. So this is a simple conversion. We have 30 meters that we ran, right? We know that 1 meter is 3.3 feet. So we do a really simple picket fence. We multiply 30. We multiply 30 times 3.3, and we get 99 feet, because meters cancel out there. 99 feet. Finally, we're going to make a distance versus time plot of our data. Let's not forget that title. So we'll call this one Mr. A's 30 meter dash. Good enough. All right. So we know on our distance versus time plots that we need to label our y and our x axes appropriately. Let's go ahead and put distance in meters, remember those units, meters, on our y-axis, and time in seconds on our x-axis. We had to run a total of 30 meters, so let's go by fives here. 5 meters, 10, 15, 20, 25, 30, 35, and then time we need to get up to 5 seconds, so let's go by half seconds. So this would be 0.5, I'm going to label 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, and 5. We know our first point, easy, that was 0, 0, right? Because we started from a stop, so we had no time or no distance. Let's then move on to our next point. At 10 meters, we clocked ourselves at 1.2 seconds. So let's go ahead and make that point. This is 1.5 here. We'll go halfway in between and then a little less. So about right there. That's pretty good. Oh, having trouble making that dot. There we go. And then let's go on to our next point at 20 meters. It took us about 2.3 seconds. So we'll put our 2.3, that's 2.5, 2.3. Let's make sure that's right. I'm doubting myself now. Oh, at 20 seconds, it was 2 exactly. Good thing I double checked. So at 2 seconds, we ran 20 meters. And then finally, it took us 5 seconds to complete our 30-yard dash. We can go ahead and draw our trend line. And we know that the slope of that trend line, or the change in y over the change in x, is equal to the change in our y variable, meters, divided by seconds. So we know that that slope must be our velocity. And if it's the trend line, then it's our average velocity. The other thing we can do is go ahead and connect those dots, and that would, so if we drew line segments that connected those dots, here I'm going to draw them in blue, what we would have, oh, that's an ugly line. Go ahead and get rid of that, those ugly lines. What we would have are line segments that show us the change in velocity for each part of our run. And the slope of those lines change. with our flattest line being here, and then two fairly similar lines for the first two segments. So we know that our velocity here in this third segment would be the slowest velocity because it has a flat slope. And then these two velocities would be pretty similar. And compared to that slowest velocity, and we know that's basically true from the calculations we made before. All right, I think that about covers it. Good luck studying. I'll see you tomorrow.